Hello everyone and welcome back to my channel. In this video, we'll cover the module Hypothesis Testing for CFA Level 1 2025. If you find the video useful, don't forget to like, subscribe and hit the bell icon so that you don't miss any update. Also in the description box, you can find the link to download this presentation and the link to join my Telegram group. Now let's get started. So there are three learning outcome statements in this module. We'll cover them one by one. Explain hypothesis testing and its components, including statistical significance, type 1 and type 2 errors, and the power of a test. So first of all, let's discuss what is a hypothesis. A hypothesis is a statement about one or more populations that we test using sample statistics. For example, suppose you are concerned with the mean of a population. So your hypothesis will be that mean of this population is greater than or equal to some amount, let's say x. So this is your hypothesis. You need to test whether this hypothesis is correct or not. So that is called hypothesis testing. Hypothesis testing is a part of statistical inference, the process of making judgments about a population based on a sample. Now let's see what's the process of a hypothesis testing. First of all, we state a hypothesis. Just as we did in this case, we state a hypothesis. Then we identify the appropriate test statistic. That means the statistic that we will use to test the significance of this hypothesis. Then we specify the level of significance. Level of significance means that whether we want a 95% confidence interval, a 90% confidence interval, or an 80% confidence interval. So that specifies your level of significance. State the decision rule. After we specify the level of significance, we get a critical value, the critical value from standardized tables. So we use that critical value to state our decision rule, that the test statistic that we calculated, that we identified here, should be greater than this amount or should be less than this amount. So that is your critical value. Then we collect the data and calculate the test statistic. Then we compare this test statistic with the decision rule here. So, and then make a decision whether the hypothesis that we stated in the first step is correct or we should reject the hypothesis. We'll cover the steps one by one. Stating the hypothesis. For each hypothesis test, we always state two hypotheses, the null hypothesis designated as H0 and the alternate hypothesis designated as HA. There are two important points that you need to remember. The null and alternate hypotheses are stated in terms of population parameters. That is, eventually you are concerned with the population parameters. And we use sample statistics to test these hypotheses. That means we are specifying the properties of a population, but we are using the sample statistics. Secondly, the null and alternate hypothesis must be mutually exclusive and collectively exhaustive. Mutually exclusive means that they should be opposite to each other. So there should not be any single value that can make the alternate hypothesis and the null hypothesis true at the same time. So they are mutually exclusive. It is very important thing to remember. Secondly, they are collectively exhaustive. That means if we collect both the alternate and the null hypothesis, all the values should be covered in these cases. That means all possible values are contained in either the null or the alternate hypothesis. Identify the appropriate test stat and the distribution. So there are different tests that we will be performing in the future. For example, if we are testing a single mean, then we should use this formula to calculate the test stat, and it is called a t-stat. The distribution is called t-distributed, and n-1 is the degrees of freedom. The degrees of freedom are required when you are checking the values of the when you are checking the critical values from the table. If we are concerned with the difference of means, then we use this formula, and it is also t distributed but with degrees of freedom of n1 plus n2 minus 2, where n1 and n2 are the number of observations in the first set and the second set. Test of the mean of differences. So these are different tests that you can perform. Test of a single variance, it's called chi-squared distribution with n minus 1 degrees of freedom. And if we are checking the differences in variances, it's a f distributed test with n minus 1 and n2 minus 1 degrees of freedom. This is the test to check the correlation, and this is the test of independence. If we have got categorical data, we use this chi-square distributed test to check the independence. So we'll cover some of these tests in the future in some examples. Specify the level of significance. So as I told you that we specify a particular level of significance. Suppose we say that alpha is the level of significance, then 1 minus alpha becomes the confidence interval, confidence level or interval. So suppose if the example says that there you have to test the hypothesis at a 5% level of significance, that means you have to find a 95% confidence interval. So let's say this is our normal distribution, this is the mean of the distribution. A 95% confidence interval means that the value lies between this, whereas this has a 2.5% probability and this has a 2.5% probability. So 95% middle values are considered in this confidence interval. So related to this, there are two types of errors. First is type 1 error, second is type 2 error. A type 1 error is a false positive. That means the null hypothesis is true, but you reject the null hypothesis. That means you reject a true hypothesis. So that is your type 1 error, a false positive. Then there is type 2 error. That means you fail to reject when in actuality the null hypothesis is false. So your null hypothesis is false, but you fail to reject. That means you accept that hypothesis. That is your type 2 error. So let's say your H0 is true, but you fail to reject the hypothesis. That means this is a correct decision because H0 is true. Then let's say H0 is false, but you fail to reject the H0. That means you have committed a type 2 error. You have failed to reject a false null hypothesis. Similarly, your H0 is true, but you have rejected the H0. That means you have committed a type 1 error. Your H0 is false and you have rejected the H0. That means you have made a correct decision. Controlling the probabilities of the two types of errors involves a trade-off. If we decrease the probability of type 1 error by specifying a smaller significance level, let's say 1% rather than 5%, we increase the probability of making a type 2 error because we'll reject the null hypothesis less frequently. Now, the significance level of a test is the probability of incorrectly rejecting the true null hypothesis. The power of a test is the probability of correctly rejecting the null. That means the probability of rejecting the null when it is false, that is called the power of a test. Now let's see how to state the decision rule. The decision rule is stated in terms of critical values. The critical values are those which are based on the level of significance and the probability distribution associated with the test stat. If we find the calculated value of the test stat is more extreme than the critical value, then we reject the null hypothesis. That means if your calculated t-stat or any test stat, let's say, is greater than your critical value, we reject the null hypothesis. And if the value is less than the critical value, then we fail to reject the null hypothesis, that there is not sufficient evidence to reject the null hypothesis. Smaller level of significance at which the null hypothesis can be rejected is the p-value. The p-value is the area in the probability distribution outside the calculated test stat. That means the smallest level of significance at which the null hypothesis can be rejected, that is your p-value. Let's cover an example where the example is concerned with the test of a single mean. Formulate and test a hypothesis that the fund's performance was different than the mean return of 1.1% inferred from the pricing model. Use a 5% level of significance. Let's first state the hypothesis. The hypothesis says that H naught, that means the mean, is equal to 1.1%, and the alternate hypothesis is that the mean is not equal to 1.1%. We'll use the t-stat. The value is calculated as x bar minus mu naught divided by s divided by square root of n. And the number of degrees of freedom in this case is 23, because we have got 24 months of data. So 23 is your degrees of freedom. The level of significance is 5% and it is a two-tailed test. That means we are concerned with equality here. So if mu is not equal to 1.1%, that means it can be either less than 1.1 or it can be greater than 1.1. So it is a two-tailed test. Now let's state the decision rule. This is the critical value from the t table. See, the number of degrees of freedom 23, and since we are calculating the values at a 5% level of significance and it is a two-tailed test, so that means in each side we have got a probability of 2.5%. So we'll check this column. With respect to 23 degrees of freedom, our critical value is 2.069. So our decision rule is that decision rule is that if we reject the null if the calculated t-stat is less than minus 2.1069 and reject the null if the calculated t-stat is greater than plus 2.069. That means the values are more extreme than the critical values. In that case, we will reject the null hypothesis. Now let's calculate the t-stat. Our x bar is 1.5% with a mean monthly return of 1.5% minus the mu naught, that is 1.1, divided by the standard error, the standard deviation of monthly returns 3.6, divided by square root of n, that is 24. So this is your t-stat. Now this t-stat is less than 2.069. So that means we fail to reject the null hypothesis because the calculated t-stat falls between the two critical values. It implies that there is not sufficient evidence to indicate that the population mean is different from 1.1%. Now let's say, what if we want to calculate the confidence interval? The confidence interval is calculated as this. The x bar, suppose we are calculating a 95% confidence interval because we are concerned with a 5% level of significance. So your confidence interval is x bar plus minus critical value times s divided by square root of n. So this is your confidence interval. The hypothesized value of 1.1% is within the bounds of the 95% confidence interval, so we fail to reject the null hypothesis. Compare and contrast parametric and non-parametric tests and describe situations where each is more appropriate type of test. A parametric test is a test which is concerned with the parameters of a population and their validity depends upon a finite set of assumptions. That means we make few assumptions regarding the distribution of the population and we are concerned with the parameters of this population. A non-parametric test is a test that is not concerned with a parameter or a test that makes minimal assumptions about the population from which the sample comes. Non-parametric procedures are used in mainly 4 situations. First of all, when the data does not meet distributional assumptions, when there are outliers, when the data is given in ranks or it uses the ordinal scale, when the relevant hypothesis does not concern a parameter. So there are different types of non-parametric tests. Tests concerning a single mean. In a parametric test, we can use t-distributed test or z-distributed test, and Wilcoxon signed rank test is an example of non-parametric test. It's an alternate to t-distributed test. Tests concerning differences between means. For parametric, we use t-distributed test, but for non-parametric, we can use Mann-Whitney U test. And tests concerning mean differences, that means paired comparison tests. The parametric test is t-distributed, but we can use Wilcoxon signed rank test and a signed test for non-parametric. Now, what is the advantage of non-parametric? The advantage is that it makes minimal assumptions, first of all. But if the assumptions of the parametric test are met, that means if your population is complying with the assumptions that we make during a parametric test, then it is generally preferred because parametric tests have a greater ability to reject a false null hypothesis. That means they have more power. So this is it for this module. I hope you liked the video. In the next video, we'll cover the module parametric and non-parametric tests of independence. Until then, keep studying and share your doubts if you have any. Thank you very much.